we'll just hold it, I guess. If you look down in there, that's where the electron beam deposition system is, right? The electrons come from one part, and then they hit your target, warm it up. That's what you're seeing through this window here, normally. And so that's where the metal is coming from, right?
Yeah.
If you look, there's a spot right here where all the metal is. This spot where it's not depositing is because that's where the shutter goes, and it's in the way, it's blocking it. But if you look down here, there's a lot of gold, and then as you come up, there's less and less gold, right? There's less and less material deposited. If you come all the way to the top of the chamber, like say right up here, it's the least amount, right? The QCO, the monitor, is right here. This is the distance it is from that source. And so that is closer to the source than our samples are, because our samples are right here when the metal gets deposited on them. And if you notice, it's got a rotation, a curvature to it. That's so that everything is all the same distance about from the source, right? And so if I was just to take that QCO, take it for its word, it's gonna say, oh, I'm growing 4 nanometers a second, right? But that's where it's growing here. If we look up here, because of the inverse square law, there's more area to cover at a farther distance to the square, right? You're gonna grow, if you're twice as far, you're gonna grow a quarter as much. Does that make sense? And so I have to tell the monitor, I'm gonna say, hey, you are twice as close, so you're growing 4 times as much material. Only tell me when I say I want to see a number that's growing on your screen, I want that number to be the sample, not you, right? So tell me a number that is a quarter as much, 0.25, right? That number is the tooling factor, right? It is because this is a tool. What factor are we growing on the actual sample versus where your monitor is? Okay? What I did was, if you look into the chamber, the QCO is actually at the height your sample normally grows at. When we actually do the growth, we move the QCO out of the way and we lower the sample down to the exact same height that the QCO is. And so the tooling factor is 1. It would normally measure the exact same number, right? Because when we do a normal growth in this chamber, we're not monitoring it. We're just going based off of the growth rate and the time, okay? That's usually good enough for almost everything someone does, right? And so what I did was I pumped up the tooling factor to as high of a number as I can. I told the tool, your QCO, it's way up here. I was lying, right? And because of that, it says, hey, I'm seeing a growth rate that is 0.19 angstroms per second. I'm actually going to tell you a number that's 4 times that, right? And the reason why I'm doing that is because if I grow 150 angstroms, I'm only actually grown 150 angstroms with my fake tooling factor. I've only actually grown about 50, a little under 50, like 38 I think it was, right? And the reason why I'm doing that is because this number right here, which I'm basing everything off of, it can only change when it ticks up to the next one. Once this goes from 243.5 to 243.6, it's going to tick up and it's going to say 7. And it's going to say that all the way up until 243.4. It's going to say 244 all the way up until it gets to 244.5, and then it's going to tick up to 245, right? And so this is the problem. Right? So we have, in the actual example, 150, 151, 152, 153, and so on. It's a continuous process. It continually adds material, but it can only tick up right here. It's going to say 150. As soon as it crosses this, it's going to say 151. As soon as it crosses this, it's going to say 152, right? So the absolute accuracy it can report is that last digit, right? Plus or minus a half of the last digit. And so what I'm doing is I'm giving it the accuracy up to 151. Because 150 over 151 right? About 1%, right? So the error we're getting, because we can't tell you 150.5, we can only tell you 150 or 151. Mm-hmm. The error you can get is about 1% from that. Mm-hmm. Regardless of the accuracy of a QCO, which is much more accurate than this, okay? So if instead we use the tooling factor of 1, which is the correct tooling factor, the number it would have reported $38, right? That's what it would have reported. But what if it was 37.511, right? Very, very close to 37. The absolute error we could have is 38 over 37. %, right? Now it's actually 3.99, the difference from this number to this number, right? So we're taking the error we could get just because it can't tell us the difference between 37.49 is going to be 37. 37.51 is going to be 38. Just because it's got that accuracy, it doesn't have an extra digit it can place here. It's going to have an error of 3%. Just because it can't tell us, right? Versus if we add that fake tooling factor, it's going to give us more digits because it's going to tell us a number that's 3.99 times as big. We've dropped that error down to 1%. Does that make sense? If you want to, when you go and you program, you can just drop that tooling factor down to 100. And it's going to tell you a number that is the actual growth rate, right? I had to divide by that tooling factor to get the correct actual growth rate. But I use this tooling factor so that this number, because normally if this was a 1, it would be that 38 number, right? All I did was use a tooling factor in order to multiply the number to get a bigger number, so there's more accuracy in the difference between that number and the one that was right before it and the one that was right after it. And then I divide back by the tooling factor to get rid of the issue. Does that make sense? It's just a trick, a tool, a skill. Make sense? Okay, so now the next thing you're going to want to do is you're going to want to actually grow on your sample, right? And so we're going to have to get the holder back out of the chamber. So the first thing I'm going to want to do is I'm going to want to take that QCO and I'm going to want to get it right out of the way. Because I'm going to have to bring that sample down, and if the QCO is in the way, if I press this down button, it's going to happily just break that arm right off. You understand? It's just another example of if you don't know what you're doing, you can easily damage this very expensive way. Okay? All right, so I moved that out of the way. I'm going to come back down to 20. Good. That's the transfer position, is 20 millimeters. And then what I'm going to do is I'm going to open the gate valve. Every time I open the gate valve, I want to check my pressures, right? I'm at 8 times 10 to the minus 7. I'm at 3 times 10 to the minus 7. We're good to open it. They're both at low vacuum, right? If this one was above 5 times 10 to the minus 5 and that one was below it, I wouldn't change it, right?
Mm-hmm.
I'm going to open this up. I'm going to push the transfer arm in. And I'm feeling for any crashes. Maybe I didn't put that at the right height. Maybe I left the QCO in the way. Any of these sorts of things could happen. Right, and I'm going to open the shutter so I can see what's going on. There we go. So, remember the locked in position? What was it?
2 markers aligned.
2 markers lined up. So I'm going to want to go back to that position. Because now if I picked it up from this position, I should be able to put it back down in this position. Make sense?
Yeah.
Okay. Now, you see the transfer arm? It's got a lower level, and then it comes up to a shelf, and then goes up to the top. Yeah? Okay, I'm gonna wanna place the sample holder right on that shelf, right? So I'll show you that again when we're out here. And so I'm gonna bring it down. If you look, you can see the pin on the sample holder.
Mm-hmm.
It's a little bit rotated too far that way, okay?
Yeah.
And that's good when you're in contact with the plate. Like if I was to bring this down, right? I'm just holding it like this. If I'm trying to bring it down and I'm trying to line this pin up and this pin up with the 2 holes on the transfer arm. If I miss, right, I can, even if I'm in contact, rotate it a bit. But very importantly, I can rotate all I want this way, clockwise, right? If I was to rotate counterclockwise, what's it gonna do?
It will fall.
It can fall right out,
Yeah.
right? And it's not gonna be in position. And so I always like to start out a little bit counterclockwise from where I wanna be so that I can then rotate it intentionally the correct direction and it should fall into place. Does that make sense?
Yeah.
Okay. So I've pushed it down, and I've noticed that the gap between the sample holder and the stage has closed up a little bit. That tells me that the sample holder, some of its weight is now being supported by the transfer arm. And so I'm going to stop and I'm going to try to rotate it into position, right? I'm only going to go the counterclockwise direction. Yeah. And so I saw the transfer arm kind of picked up. And what that means is I've been supporting some of the weight here, and this pin hasn't quite lined up with the hole, so it's pushing down on the transfer arm. And then once it lined up, it fell into that hole, the transfer arm kicked up into position. So now I know I'm in position. I'm gonna rotate Oh, it's not letting me. There we go. It's still the sample holder looks like it's on the arm, and I've managed to go from the two things lined up with each other to just the screw, which is the unlock position. And now what I'm going to try to do is lift up the stage, and hopefully the sample holder is going to stay on the sample arm, the transfer arm. Yep. So now I'm going to go all the way up to 20 millimeters. There we go. Now you'll know this is closed by it'll stop, and you should always, if you can go farther, it'll click over like a torque wrench.
Yeah.
Okay. That's how you'll know it's closed. And we can go ahead and turn the load lock pump off, and we'll wait for it to come up to atmosphere. Okay. Recipe, and I found 193 angstroms, or 0.193 angstroms per second.
Yeah.
And I just ran it today, and it was 0.19. It's 3 out of 200. 1.5% difference. It's not a big deal, right? Because we're saying, well, the QCO, it only really has like a 10% accuracy to begin with. And so if you really cared about the actual thickness of your sample within a few percentage, you're going to want to take this number, grow however thick of a sample you need to then take and go to a different measurement technique. Maybe profilometry, you'll have to grow a couple hundred nanometers, right? Maybe if you use AFM, you'll have to grow like 10 nanometers. And you'll use AFM to measure your actual thickness, and you'll calibrate it, right? You'll say, oh no, the growth rate's not actually 0.190, it's, 0.2 or 0.18 or something. But if plus or minus 10% is good enough for you, and I'm not saying plus or minus 10% every time, I'm just saying that the actual versus what you grow could be different by 10%. You should do that calibration. But if you're able to accept that difference, I'd recommend just kind of going with it. And so your platinum growth, that you're going to grow that really thin one, I'd recommend doing AFM because your thickness is a really important variable to know. But at the end of the day, if you grow 4 nanometers versus 5 nanometers, both of them will probably work for your process. You just want to know what it is, right? And so this process should grow the same thickness every time. It's just that the number we come up with isn't a perfect number, right? So if we follow this recipe, we think we're going to grow 0.19 every single time, but maybe we grow 0.18 every single time, and it's 0.18 plus or minus a small error, but 0.18 is pretty far away from 0.19. You see? It's 5% off. But the actual difference run to run might be only off by 1 or 2%, right? And so it would be the 0.18, I'm just guessing, plus or minus 2%. But I don't know what the actual number is. It could be plus or minus 10%. You see what I'm saying? Okay. We've come up to atmosphere. Now, during the platinum growth, I left the rotation off. And so you can see this is where the QCO was. It was blocking the sample from getting platinum grown on it. And you can see where that blockage happened. Okay? When you do a normal growth, you want to have rotation. And there's no real good way to see it here, but there could be variation across the sample, like from this side to this side. Just from your platinum is growing over here and it's aiming kind of at your sample, so this side is going to grow faster than the far side. And so if it's like this in the chamber, this side's going to get more platinum than that side. But if you rotate it very slowly, over your 10-minute growth, it might rotate 200 times. And so the variation from one side to the other is going to be much smaller. Because it'll grow smaller here and more there, smaller here, more there, and as it grows around, it'll get more and less and more and less, and that'll average out. Okay? So now what we want to do is we want to grow on one of your samples, right? Do you want to do that today, or do you want to do that another day?